What specific problem does the deliberate practice, DP framework aim to solve in the context of synthetic data generation?
The deliberate practice, DP framework aims to solve the problem of inefficient training with synthetic data by dynamically generating only the most challenging and informative examples, rather than relying on a static dataset. Traditional approaches often generate a large pool of synthetic data and then prune uninformative samples, which is computationally inefficient and can lead to diminishing returns in performance. DP addresses this by incorporating a dynamic loop between a diffusion model and a learner, where the learner's prediction entropy guides the generation of new data points only when performance stagnates. This ensures that the model is continually exposed to increasingly informative data throughout training, improving scaling laws and overall training efficiency. Ultimately, DP enhances the effectiveness of synthetic data generation by focusing on the informativeness of samples, thereby maximizing learning efficiency.
How does the proposed deliberate practice framework work? Could you illustrate its step-by-step process from initial data generation to the training of the classifier?
The deliberate practice DP framework begins by generating an initial set of synthetic training examples using a pre-trained generative model, which samples images in a class-conditional manner. The classifier is then trained on this initial dataset, entering a learning rate warm-up phase. As training progresses, the framework employs a patience mechanism to evaluate the classifier's validation accuracy at regular intervals. If no improvement is observed, new data generation is triggered. During this phase, the framework generates additional examples guided by the learner's prediction entropy, ensuring that only the most informative and challenging samples are added to the training set. This iterative process continues, dynamically augmenting the dataset and resuming training until a cooldown phase is reached, where the learning rate is decreased and no further data is generated.
Can you provide a simple example to illustrate how the entropy-guided sampling works within the DP framework? Walk through the main steps with a hypothetical scenario.
In the deliberate practice DP framework, entropy-guided sampling operates through a dynamic process that adapts to the learner's performance. For instance, suppose we start with an initial set of synthetic images for a classifier. After training the classifier, we monitor its validation accuracy, and if it plateaus, we assess the learner's prediction entropy to identify which examples are currently challenging. Let's say the classifier struggles with certain classes, leading to high entropy values for those examples. The DP framework then uses this entropy information to guide a diffusion model to generate new synthetic images that are specifically challenging, thereby augmenting the training set with these high entropy samples. This process repeats iteratively, ensuring that the classifier is continuously exposed to increasingly informative data, ultimately improving its performance on real validation sets.
What are the theoretical benefits of using the DP framework over traditional static data generation approaches? In what ways does it improve efficiency or accuracy?
The deliberate practice DP framework offers significant theoretical benefits over traditional static data generation approaches by dynamically generating synthetic data based on the learner's performance. This method leverages the learner's prediction entropy to focus on generating challenging and informative examples, which enhances the scaling behavior of synthetic data training. Theoretical analysis shows that selecting hard examples improves scaling laws, leading to reduced test error and requiring fewer training samples for the same performance. Empirically, DP has demonstrated superior performance on datasets like ImageNet 100 and ImageNet 1K, achieving higher validation accuracy while using significantly less data and fewer training iterations compared to static methods. Overall, DP's adaptive mechanism ensures continuous exposure to informative data, thereby improving both efficiency and accuracy in model training.
How was the effectiveness of the DP framework validated in the experiments? Discuss the datasets used and the metrics evaluated in the testing process.
The effectiveness of the deliberate practice DP framework was validated through extensive experiments on two datasets, ImageNet 100, and ImageNet 1K. In these experiments, the DP framework was compared against static data generation methods, where all data is generated before training. The validation accuracy was tracked throughout training, and the performance was evaluated using a fixed small validation set of real data, with the real training sets serving as held-out test sets. Metrics assessed included validation accuracy and generalization performance on out-of-distribution datasets, such as ImageNet R and ImageNet Sketch, where DP demonstrated improvements of up to 15% over models trained with real data. The results indicated that DP not only required significantly less synthetic data and fewer training iterations, but also achieved superior performance, confirming its effectiveness in generating informative examples dynamically.
What specific results were achieved with the DP method when compared to prior work? Highlight the performance improvements in terms of data usage and training iterations.
The deliberate practice DP method demonstrated significant performance improvements compared to prior work on synthetic data generation for image classification. Specifically, on ImageNet 100, DP generated 4.6 million fewer samples and completed training in only 1/6 of the iterations used in previous methods, yet still achieved superior performance on real data. Similarly, on ImageNet 1K, DP reduced sample generation by 56.2 million and cut training iterations by over 30%, while outperforming previous results. These results indicate that DP not only enhances the efficiency of data usage, but also accelerates the training process, achieving better accuracy with substantially less computational effort. Furthermore, DP exhibited strong performance on out-of-distribution datasets, surpassing models trained with real data by up to 15%.